Hi, welcome to one more video on MOSFET amplifiers. So in this video we will see the active load CS amplifiers. We actually try to simulate these active load CS amplifiers with different load conditions, and we will also verify what is the voltage gain of the amplifier and its input and output impedances. Let us consider this circuit. So I have applied an input voltage to this. Okay, let me change this to V in so that the readability is fine. Let me change this to some VB. This is fine. So these are all the this is DC voltage, this is a sine wave, and if you can observe here, I have applied a sine wave with a DC voltage of 0.6, that is VGS of this MOSFET is 0.6. And first we shall see what is the design of this, what are the specifications we are assuming, and the device specification that we are considering for this particular amplifier is NMOS will have these specifications, Kp, VTO and the lambda values, and similarly for PMOS these are the values. And of course this is a parameter, or this is a statement to vary this resistance R1 having a value RVAR. From these values we'll just discuss all these things when we actually take up the entire simulation process. So this is the circuit what we are looking at. So this is the input where you are applying. So this is a NMOS transistor, this is a PMOS transistor. So the specifications are, we are designing this amplifier with a drain current of 1 milliampere. We are assuming the overdrive voltage of both the MOSFETs as 0.2 volts, that is 200 millivolt is the VOV. Of course we know that VOV is nothing but VGS minus VTH. So since VTH is equal to 0.4, then VGS of both the transistor has to be 0.6. So that's what is the VOV stands for. And we are also assuming one more condition, that let the DC voltage at this point be 0.9. So why this should be at 0.9 is because that is half of your VDD, which is 1.8. So just to understand this, try to just have a look at this now. Let me just suppose if this is your output possibility 0 to 1.8. So my output voltage, if it is centered at 0.9, so I can able to effectively utilize the swing here. So now since I have a circuit something like this, since I have a circuit which is now I should apply DC voltage here. So this is VDD, this is a PMOS transistor, this is NMOS transistor. Here I am applying the input voltage Vin, here I am going to measure the output voltage. So even though I am measuring the output voltage here, this is going to have a DC of 0.9 volt. So that's what is this DC. When I apply a sine wave, I will get an output waveform at 0.9, which is inverted. So which will be like inverted. So this is centered around 0.9 volts. And what is this amplification? That depends on, so if I say this as M1, this as M2, since lambda is non-zero, this will have a resistance R01, this will have a resistance R02. So what we are assuming is, and of course the VOV, which is nothing but VGS minus VTH, we are assuming this to be for 0.2. So that for this MOSFET to keep it in saturation, I should dedicate 0.2 volts. So that is, so this 0.2 volts is dedicated for keeping this MOSFET in saturation. Similarly on the top, I should dedicate 0.2 volt at the top too. So I have a actual swing from 0.2 volt to 1.6 volts. So it's effectively 1.4 volt swing I have. So this is 1.4 volt swing that I have, centered around 0.9. So you have okay, now since it is you have 0.7 there, you have 0.7 volt swing. So you have almost 1.4 volt swing available, because we are assuming VOV of 0.2 volt. So let us again go back to this and try to find out what is the WL of this, of those things. We know that this is expression for drain current and the saturation condition with lambda non-zero. Suppose if you substitute all these parameters, because I know what is ID, which is 1 milliampere, I know what is VGS, because this VGS minus VTO should be 0.2, so naturally this VGS has to be 0.6, and VDS, that is the drain to source voltage, should be, if you are assuming this to be 0.9, suppose if you see here, suppose if you want to have this to be at 0.9, since it is 1.8, so this voltage is 0.9 and this voltage is also 0.9. So VDS of both the transistor is equal to 0.9 volt. So in that expression of this, so I am substituting VDS as 0.9 because this voltage is at 0.9 volts. So upon substituting all these things, suppose if you calculate this omega by L of first transistor M1, so this comes out to be 247.7. So I just want all of you to just, I will just pause now for a few minutes. So just edit, enter these values in your calculator and then find out what is the W by L. So just substitute it as 1 milli, alpha equals half, Kp is Kp of n, which is 200 micro. This put it as unknown, that is alpha A. This is 0.2 whole square, open the parenthesis, 1 plus 0.01 into 0.9. Do shift cal, you should get 247.7. So let me just do the first one along with you people, so you can just see now what I have is, okay, let me just put this aside. So I have these values, 1 exponential minus 3 alpha equals, that is 0.5 into 200 exponential minus 6 into alpha A into 0.2 whole square into 1 plus 0.01 into 0.9, close the parenthesis, shift calculate. So do you have now 247.7? That's what is this 247.7. Okay, with these specifications I got it as 247.7. Now this is W by L ratio. If length of the first transistor is 10 micron, then naturally the width of first transistor becomes that into 10, that is 247.7 into 10, which will be this much dimension. Similarly, I have to find what is the WL of this, and I should know what is the bias voltage that I should be connecting here, or I should be connecting here. So for that, so this is the expression for your P transistor. So since the current will be negative in the direction compared to your NMOS, we are taking simply the magnitude of ID of PMOS transistor, which is half of Kp of P transistor, because we know that the Kp is mu into Cox. Mu n will be larger compared to mu p, so that's why we are assuming Kp of PMOS transistor is half of Kp of NMOS transistor. So please note this, and of course what we are trying to find is what is WL of 2 here, and this VGS magnitude minus VTO magnitude is again 0.2. So you can see this is what is 0.6 and 0.4. These are the magnitudes, and if you substitute all these things, even lambda is 0.01 and VDS is 0.9 volts. Upon doing the calculation, if you find WL of 2, since only difference from ID of N to ID of P is only this Kp of N and P will differ, so all other things remain same. So for that, WL of 2 is, okay, ratio of WL of 2 is 495.5. Okay, with this assumption you will end up with this. Now the question is, what is this bias voltage? What is this VB? So actually VGS magnitude is 0.6, but what is VGS for the PMOS? It's usually always negative voltage. So this VGS is nothing but minus 0.6. So what is VG now? voltage, because we can write VGS is nothing but VG minus VS. So what is VG? If you see, this is your gate voltage, it is connected to VB, that is some voltage, and the source is connected to VDD. So that's why we are writing it as VB minus VDD is equal to 0.6. So upon doing all these things, you will get VB as VDD minus 0.6, which is 1.2 volt. Meaning, if I connect 1.2 volt here, which is the gate, and since the source is at 1.8, then what is VGS you are going to get? VGS will be minus 0.6. So that's what I'm looking for. That's what is I'm looking for a PMOS transistor. So please carefully look at this. Why this VB should be 1.2 volt? VB should be 1.2 volt. So that the difference between gate and source should be minus 0.6, because I know that 1.2 minus 1.8 is minus 0.6. So with these specifications, let us do the simulation. Let me show you the simulation now. Do we have the same circuit being rigged up here? Seen it? So whatever DC voltage that is required for this has been edited here. That is, this is my DC voltage, and of course this is my input voltage, all those stuff. And you can see this is VB, and I have a transistor dimension. This is 10, this is 2477, which is exactly here 2477. And for the PMOS, I have the dimension as you can see, this is my dimension. This is 10 micron and 4955. This is 4955. So these are fine. So let us because for this circuit, let us find out what is AV, and that is voltage gain, and this one. So voltage gain as per the circuit, if you see here, the circuit has got of course voltage gain is minus GM1 into R01 parallel R02. That's what the expression is, and of course R out is given by this. So if you try to find the value of GM1, so which is given by under root of 2ID Kp of n into WL of 1, it comes out to be 9.95, and of course this R01 R02 will be what is this, 1 over ID into lambda, which will be 100K. And let us see, are we getting the same value? So we are supposed to get 497.6 as the gain. So let us see whether all the conditions are okay here or not. So before we actually start doing the simulation or start verifying the gain and all those things, let us ensure that are the MOSFETs in saturation, or what are the DC conditions for that. So we know that the DC condition that you have to select is this is DC operating point. If I run now, so let me see what is, go to this view, see here. Now C is the NMOS current and PMOS currents are 1 milliampere. This is 1 milliampere, and VGS of both of them is, of course this is 0.6, this is minus 0.6. VDS is of course we expected it to be 0.9, it's 0.91, fine. And of course threshold voltage is minus 0.4, and VDS sat, of course this is fine. Can you see now this is GM? So GM is 10 millisiemens, and this is GDS. So this GDS is actually 1 over R0 value, 1 over R0 value. So this says that if you can carefully see this, since VDS is more than VDS sat, so VDS sat is supposed to be 200 millivolt, but you have VDS as 0.9 volt, which is far more than required saturation current, and the same thing is for the PMOS also. So both the MOSFETs are in saturation. Now since we verify that both are in saturation, let us apply the input voltage. Of course we already applied. Let us see the input voltage and output voltage. For that I have to do the transient response. So this is my transient response. So since the frequency is 10 kilohertz, let me see around 10 cycles. To see 10 cycles, let the timing be 1 millisecond. Let me start from 0 in time steps of 1 micro. So this will guarantee me 10 cycles of input and output. Now you can see I have this. Let me just see, I think what has happened. Let me just go back there. Okay, if I run it now, let me see what is my sine wave. This is, of course, I know the input voltage is shifted by 0.6, and there I'm applying the input voltage, and this is my output. So I'm not too much interested in the input. So let me just take out the input here. How do I take out? You delete it. Okay, sorry, I deleted the output. Let me again do it. Now this, I'll see. Fine. Now you can see actually you are seeing two waveforms. So why I am seeing two waveforms is, so let us okay, for the time being what I'll do is, let me just delete this. Okay, let me cut this. Okay, let me just take out this and then run it again. Okay. Let me just